Hello, hi everyone. Welcome to this talk. I'm here to talk to you about our project called SEMA, which stands for Scalable Instructable Multi-Worlds Agent. Kind of a mouthful, but SEMA is fine. Just before I do that, a quick introduction on who am I and who Daniel is. I worked in the games industry for about 15 years, started at Square Enix, moved to Sony PlayStation. I looked after the TRC and technical requirements, which I think is a very loved subject in the games industry. Recently became a dad, and also I spend my very limited free time trying to get good at Elden Ring, not very successfully. Daniel has been a research engineer at DeepMind for the last 5 years, building AI agent, and before that he was also in the games industry working on Championship Manager. So what do we think about when we hear AI? The word AI is obviously robots. There have been few challenges as to why the robots are still lagging behind in the AI universe. Some of these challenges are obviously challenges related to the physical embodiment of an agent. It's also very expensive. Every robot is a considerable amount of money to invest. There is a difficulty in gathering a diversity of experience. Often you are restricted to robotic labs, which do not provide as much variety as you would like. You have also limited control over experience. There is scientific evaluation that is quite rigorous and challenging in non-labs. And finally, there are safety considerations because you want to make sure that the robot is okay. This is just context to give you an idea of why we decided to go with SEMA idea, with the SEMA thesis, and why we did that. In 2020s, the AI world is dominated by large language models. So you have obviously ChatGPT from OpenAI, you have Gemini from Google DeepMind, and also Anthropic with their model Claude, and more of them. They're really good. They're really good for the use case. They can generally do programming assistant. They can do question and answer. They can do some answering based on, for example, movie frame and things like that. They have also long context and so on. Together with text, large language model, you have also image, video, and audio models that currently are able to generate images and storyboard. They're used for music. They're used for maybe in the future full-length movies. However, what this model do not have is something that we call, they offer a disembodied version of the AI, so they're not embodied. What do we mean by that? Embodiment is essentially the degree to which a system can affect and control its sensors. Embodiment in the larger sensor space can also have different states, which we call task. Current system, like I said, they are very good in the digital realm. However, in the embodied and the physical realm, they are not that good. We wanted to create an embodied version of an agent with SEMA, with the SEMA work, and this is why we took the road that we took. From a biological neuroscience perspective, this is a bunch of reading. We know that the common theme, the brain, is one of the main purpose of the brain is to coordinate the body movement. However, there have been 5 known breakthroughs in our history for the functionality of our brain. One is the steering, that basically is the foundational breakthrough for everything else. Learning from direct experience, describe a learning mechanism where we adjust the behavior based on direct experience. After that, you might be familiar with the next one, which is called reinforcement learning, and it comes directly from the steering, and basically the ability to do an action that is based on reward of that action. We then move on to mental simulation, and then mentalizing, and also language, which is only well, self-explanatory. However, what I want to make sure is that steering is well known as the very first and fundamental of this breakthrough, and that we on CIMA focus directly on experience. Now, if we take a look at the previous scenario of games and simulated environments in AI, we start from deep reinforcement learning, Atari, when we developed the algorithm that was able to play and successfully master all the Atari environment in early 2010s. We then move on to some other breakthrough like Minecraft and Doom. You had agent playing Minecraft and other games. And then we move on to the late 2010s, which saw other agents performing particularly well, for example, on StarCraft 2. Now, all of this, from the very beginning till the end, represent an increasingly complex trajectory. There are more observations to take care of. There are more actions. There are more dynamics. The environment gets more and more complicated, and so on. However, any breakthrough that is associated with this usually remains single domain. So you can have an agent that surely is very good at completing the game of Atari, but it's limited into that world. Same for StarCraft 2, same for other games. Is also affected by limited number of tasks and limited number of task specification, which means what can you do inside that environment, unless you just play to win the game. This was the original user interface agent. So you have a multi-domain, and then you have the agent and that plays the game. So there were limitations, like I said. You had the universe of Atari, which was great because the agent learned different environments. However, the task specification, which means what can you do in the environment, is always win the game. On the other hand, you have the Minecraft breakthrough, which was great in terms of task. You had an agent building whatever you can build in Minecraft. However, was very environment specific, was able to do all of those things in Minecraft only. So what we did was we went for both. We thought there were positives in both approach, and so we decided to combine and see what we came up with. What we developed is a general interface for real-time interaction. The CIMA agent it takes goals or instructions in natural text from a human user. The agent perceives the world through the screen in real time. It does not have source code access. It does not have API access. It plays exactly the same as a player would play. And the agent controls the game, like I said, using keyboard and mouse input. There is no difference between a human player and an agent. We took no shortcut, and that was a lot of fun. As you can see, this is essentially a frame from a short video from No Man's Sky. The agent is essentially pressing the right button to move and to board the spaceship and then fly away. This is real time. Like I said, there is no secret API. At DeepMind, at Google DeepMind, we played with games, we used games for AI testbed for a very long time, 14 plus years. Pretty much every breakthrough we had was associated with games. We strongly believe that games are fantastic testbed for AI training. They are safe, they are contained, but they also offer immense variety. They offer a large space, so it's great. Games are in our DNA. Our CEO, Demis, has been a game developer before, Syndicate and Theme Park, just to name some. And also, a lot of the people working at Google DeepMind come from games industry. Like I said, myself, PlayStation, but we have pretty much everyone. So we really value the games craft and what goes behind creating a game. We know how hard it is. We've been there. So we decided that for this project, we would reach out to some studios. Now, the criteria based on which we selected the games, Daniel will go through it later on. However, we decided that we needed to engage directly with the games industry and gaming community, and so we started reaching out to some of the studios that would fill our criteria for game selection. Incredibly enough, they were all very receptive. They were all very nice. We described to them what the overview of what the research was about, and all of them agreed to let us use their games. I must say, one of the best meetings I've had since starting working has been the one where we decided to go for Goat Simulator 3 in a room full of researchers, very excited about the scope of Goat Simulator 3. So this is just a showreel that displays some of the games that we went for. They're all available on the blog post we released. And essentially, what we did was to train the agent on those games, and then, like I said, Daniel will go in detail about what the results were. My last slide is this short clip that shows what some of the result of the agent playing some of this game. You would see Valheim, you would see No Man's Sky, and others. And those are instructions that are given to the agent, and the agent performs the action that it was requested by the user. You see Satisfactory, Teardown, and others. So thank you so much. Now it's Daniel.
All right. Thank you, everyone. Very glad to be here. So I'm now going to talk about Simmer, which is Simmer is, Pierre has already said, it's a scalable, instructable, multi-world agent, and we have kind of a little tagline for what the precise goal for Simmer is. So it's a single agent with a universal interface that can be instructed via language to perform any task in any 3D visual environment. So let me unpack that just a little bit. So we have a single agent. We have universal interface. So as Pierre-Marie mentioned, that is keyboard and mouse. So it will play a game exactly as we would play any computer game. There's no advantage to the agent from the internals. Instructed by language. So there are two input channels to the agent. One is the visuals from the game. The other is a free text channel. A user can put in any text stream. Then we have any task. There's a whole field of literature defining what is a task, and it's a really, really interesting field and goes into incredible depth. But colloquially, we can define a task as just some kind of goal within the game that a user might want performed. We have here No Man's Sky. There are little tasks like getting into spaceships, using the jetpack, things like that. And then any 3D visual environment. So we want this agent to work across essentially all 3D environments. We initially started with some subset of all. So now I'll go a bit more into the parts that make up Simmer. So we have the environments. We have the data. So we initially started training. We started by collecting lots of data of people playing the different computer games that we could have. And then when they're playing, we're collecting all the visuals from the screen and also all the interactions they have. So we get all the key presses with which we can train the agent. So we have an agent training process. We also use some pre-trained components, which are represented by the little cogs that are in there. The agent is purely trained at the moment via behavioral cloning. So it's seeing the visuals and the keyboard and mouse actions from the humans, and it's just trying to exactly imitate them. At this point, there's no reinforcement learning in the process. And then the training process produces an agent. We then take that agent, we put that back into the environments. So we get the agent to play the different computer games, and we evaluate it. And we'll go a bit more into that a bit later. So first, a little bit more detail on the environments. So what were we looking for in our environments? We wanted to target 3D because we had reason to believe that things would generalize a lot better in 3D than 2D. And also 3D is the same number of dimensions as our world. We wanted third or first person, again, for a kind of more embodied kind of experience. If you have a very high up kind of 2D, a 3D game where it's essentially like 2D because the camera is really high, it's not necessarily going to generalize very well. And then we wanted a complex open world environments. So there's lots of great games where you have very specific goals, but because we want to train agents that learn kind of any text instruction, we want environments with lots of broad goals for the agent to do, not just kind of, kill the next boss, get to the next checkpoint, things like that. Other things that are nice to have, so interesting to humans. This is a good thing about commercial computer games. They've been built to be interesting to humans. We assume humans are interested in it. Humans do spend their time playing games, I've heard. Not violence focused, so some of our games have a little bit of violence in Valheim, you kill monsters and stuff like that. But we didn't want that to be the focus of the agent. We were kind of more interested in a broad range of skills. And then diverse, we want each new environment to be different from the previous ones and to test our agent out on new sets of skills and have new kinds of things that they can do within it. So these were the video games that we initially partnered with. So briefly, Goat Simulator 3, I assume everyone's heard of. Hydroneer involves lots of challenges around manipulating water and things like that. No Man's Sky, Satisfactory, Teardown, Valheim, and Wobbly Life. And this gave us like a good diverse set of places in which we could test the agent. We also had these research environments. So 3 of these were environments that were built internally for previous projects they're all, so to take Playhouse, for example, these are also kind of 3D embodied environments. And in Playhouse, you have either a kitchen or a messy bedroom, and the agent is tasked to do things like make a sandwich or clean up its room, things like that. So kind of, kinds of tasks that might relate to a human world. And then also Proctor, which is an external research environment. So next piece is the data. So we initially focused on getting humans to collect all the data to scale up and be the training set for the agent initially. There were 2 ways in which we collected data. The first was one-player annotation data. So we'd just get humans to play the games for, say, an hour at a time. We didn't give them any specific goals. It was just kind of go out, enjoy yourself, kind of do things that seem interesting to you. And then we recorded all the video and the actions from that. And then after the fact, they had a little GUI tool where they could go in and just kind of mark in text describe what they were doing at different points in the game. So, here I was collecting wood, here I was adding the wood to the fire, things like that. And then we also had a 2-player setup where essentially one human would act as the agent. So they would be trying to do these small, short commands that were given to them by another player who would be acting as what we called the director. So the director would be given some high-level goals, such as build a house. And they weren't supposed to tell the high-level goal to the person playing as the agent, but they would have to break the whole high-level goal into sub-goals. So if you want to build a house, you might need to collect wood, level the ground, put up a wall, things like that. So we collected some data like that. In the end, we ended up collecting a lot more of the 1-player data. We found that data was a lot richer. And also, it kind of wasn't very fun for the players, the 2-player setup. Like, it's not actually very fun playing a computer game by typing text and asking someone else to play the game for you, turns out. So with all this, we collected what ended up being an absolutely vast data set. And this contained a huge kind of broader range of things that people did. So this is just a little chart kind of showing some of the kinds of skills in there. So you can see headbutt is on there, which almost certainly comes from Goat Simulator 3, we assume. But also there's navigation skills that are very common across games. Things like farming, lots of diverse skills. And in the end, I think we had like most of the verbs that you would find in a dictionary, most of the commonly used verbs in the English dictionary were present in our data set. So the next part is the agent. So again, we have a simmer agent. It's taking actions via keyboard and mouse with the environment. The environment is running in real time. So we do have to consider that the agent needs to be fairly performant. There are certain sizes of agent we probably just couldn't use because they'd be too slow for the environment. The environment sends out visual input that goes to both the agent, but also to a user who can then prompt the agent via natural language to do the thing they want done within the environment. So specify some kind of task. And then just to zoom in a little bit more on the agent. So it has this visual input. This visual input goes first to a Spark encoder. So Spark is a project released, I think, a year ago or something by Google. and it's trained on a vast amount of data from the internet. So it tries to pair images with the language describing that image. And this one is also fine-tuned to have a bit of spatial information. So we use that to encode the kind of raw pixels into some encoding that should represent the language content of the image, and then roughly kind of where on screen things are. And then we also have a video encoder. So this one is Funaki, which is another Google internal one. And that gets given the last 11 frames that the agent has seen. And so in that way, the Spark encoder encodes the current frame, and then Funaki encodes like the motion that is going on in the agent's environment. So that'll give it an idea of if it's moving forward, if it's moving backwards, maybe other things that are moving in the environment. There's also the language goes through a text encoder. That's just an internal one. That all goes through a multimodal transformer, which is the kind of thing that's commonly used in large language models. And then the output is keyboard and mouse policy. And we used a thing called classifier-free guidance. This was one of the most impactful things we actually used in the project. So just very briefly, what classifier-free guidance is the agent has not just one output of keyboard and mouse actions, but two outputs. One is the output conditional on the language that's received, and the other is an unconditional output. So that's the action that it would take if it didn't have access to any language. So just a kind of a rough average of the kind of actions an agent would take in that kind of state, in the state that it was in. We then take the conditional output, we subtract from it the unconditional output, and we add that to the agent's conditional output times by some hyperparameter. It's a little hard to see there, but there's kind of the equation there. And this basically pushes the agent into a much more language conditional area of its action space. So it's trying to remove the kind of average of what it might do in this position so that it's really, really language conditional. And there'll be more results on that a little bit later. The next part is evaluation. So the building block of evaluation is what we call a task. So a task has three things. It has a state. So for example, here we see the kitchen within the playroom. It has some kind of instruction, such as, well, here it's put the frying pan on the stove, and then some kind of success criterion. And then we organize these tasks into challenges, which are collections of, say, 500 or so tasks. We have one challenge per computer game that the agent was trained on, and then a few challenges that go across skills between games. So for example, we have a menu use challenge to see how the agent uses menus between different games we've trained it on. The way we actually judge success in these is there's three different methods. So for our internal environments, the good thing is we actually built those in Unity, so we have access to the game internals. So if the agent is asked to, say, pick up a red pen, because we actually have access to the game internals, we can just see the position of the pen and see if it gets raised up. And if it does, we can signal that the task is a success. But the agent never gets access to any of these internals. It never sees the reward itself. It's still just doing behavioral cloning. The next way we can judge success is using optical character recognition, or OCR. So most commercial video, well, not most commercial video games, of the commercial video games that we have, a lot of them have like text on screen when certain actions are performed. So the video here, the agent is tasked to collect raspberries, and we know that when an agent collects, when you collect raspberries in the game Valheim, a little bit of text saying raspberries pops up, and so we check that bit of text and we see when the text comes up, and when it does, we give a reward. And then the final way in which we judge success is human evaluation. So there are lots of things that you might ask an agent to do in a computer game where there's not going to be text that comes up. For example, going upstairs. And so the gold standard is we can actually just record videos of the agent, put them in front of humans, and ask them, did this thing happen? And that allows us to get all the remaining kind of skills that we might want to test for. So now that's the setup of Simmer. And so now moving on to the results that we got. So first, before we go into the exact numbers, we can talk about some of the qualitative results. So there's a whole bunch of behaviors that are very general across environment, mostly kind of navigation and things like that. Every environment has some navigation component. And so what we can do is we can take our agent, we can give it the same prompt across environments and see how it does. So for example, we can ask it to go forward and see that, yes, it does a pretty good job of going forward in different environments. although these videos are lagging a little bit, so it's maybe not the most smooth, but the agent does go forward. We can also ask it to turn left, turn right, other things like that, and it does a pretty good job of following these basic commands across all the different environments. And I should remind, this is like the agent responds pretty well to kind of any text input. So here we've said go forward, but you could also say move forward, step forward, make yourself be further in, make yourself go forward, those kinds of things. And then there's also menu use is another thing that is in common across environments, and the agent does a pretty good job of opening the menu across environments, but our internal environments don't have menus, so there's no video there. So the other thing we might want to look at is how does the agent do with game-specific behaviors? So, for example, No Man's Sky has a spaceship in it, which isn't in the other game, so we can ask it to go to the spaceship, and it does a reasonably good job of that. We can ask it to use the jetpack, that's a No Man's Sky specific item, and also once it's in the spaceship, it can shoot asteroids. It seems pretty good at doing that. When it comes to Valheim, it's very good at collecting things within Valheim. There's also menus. It can do things like craft clubs. There's also Greylings in Valheim, and it does a pretty good job of fighting Greylings. It seems to enjoy fighting Greylings. Goat Simulator, again, there's a whole bunch of very specific Goat Simulator stuff. But it includes when you ask it to go to the Goat Castle, that's a specific thing within Goat Simulator, and it seems to do a pretty good job of knowing what a goat castle is and getting to it. And there's similar kind of specific skills in lots of the other games that we've looked at, but it seems to do a reasonably good job of. There's also some things where there's commonalities across domains, but like the specifics vary a little bit. So for example, most of the games we have some element of like vehicles or using vehicles. And so in Valheim, in No Man's Sky, it's go to the spaceship. It does a pretty good job of spaceships. Driving the tractor in Goat Simulator, it knows what a tractor is. It can get in a tractor, get in the blue car, get in the purple car in Wobbly Life, get in the boat, get in the truck, I think that is. And it's pretty good at understanding these different vehicles and kind of getting into them and driving them a little bit. So now the actual kind of like quantitative results, so the actual score that we got. So obviously this is very, very dependent on the tasks that are chosen. So all of these are kind of in the hundreds of tasks for the different challenges you see here. So these bars are like the score on Playhouse, the score on World Lab, score on Satisfactory, etc. And the color shows what kind of evaluation we were doing. You can see, so again, I want to kind of put this in a little bit of context. Like this is an agent playing a game, given any text instruction and being able to follow it. So it gets to, it does reasonably well, but there's also like a lot of instructions that it can't actually follow. But this is enough to say if you put a random agent through this, it would probably get 0. Like, these are all kind of non-trivial things to do. So as well as the kind of performance across games, we can also look at the performance kind of grouped by the different skills involved. So you can see, okay, so it's very good at stopping because obviously stopping is a fairly easy thing to do. You just do nothing for a little bit, it learns to do that. But there's also skills like driving and things like that where it seems to do pretty well at those kind of things. So the one it struggles the most at is building, and one of our hypotheses is the agent really struggles with tasks that require more precise control, and that might be something where we need to work on in the future. I'm now going to present some ablations. So in the next slide, I'm going to show a few different graphs, and I'll just go through what are the different things that are going to be in there. So the first thing we're going to have is the simmer agent. So that's an agent that is trained on all the different domains we've talked about, and then evaluated on all of those domains as well. It also has pre-trained components, which are represented by the little cogs in the blue box, and it takes language as its instruction. The next thing that we're going to show is environment-specific agents. So these are agents that are trained just on the data from a specific environment and then evaluated just on that environment as well. So for example, trained just on Goat Simulator 3, evaluated just on Goat Simulator 3. And when we show the graphs, everything we show is going to be normalized to set the environment-specific performance to 100 across the board. So this way we can give an idea of like how much better or worse different ablations that we do are than a kind of an agent specifically tuned to an environment. You can also think of the environment-specific agent as being what you'd get if you trained an expert on every single domain and then just had a switch statement saying, if the game is X, go to game, use agent X. The next thing we're going to show is a zero-shot agent. So the zero-shot agent is trained on all but one domain and then evaluated on the held-out domain. And this will give us, say, an idea of how the agent behaves in some environment it has never seen before. And this maybe gives us an idea of how the agent might behave if we put it on some new game that we've not onboarded yet. And then the next thing is an agent with the pre-trained components removed. So I mentioned we use a bunch of pre-trained components. These pre-trained components obviously have access to kind of internet data. They know a huge amount about the human world and what the objects are in it. So it's interesting to see how an agent does if it doesn't have that kind of base of background knowledge. And then the next ablation is a no language ablation. So this is where the agent is going to be given a task, but it doesn't know what the instruction is that it's supposed to perform. And this is mostly just a sanity check to see, we expect the agent to do very bad without language. But for some of the tasks, you can kind of guess what you're supposed to do by the context. If there's only a single car visible, you probably should get in it. And the last thing we're going to show is how humans do on these tasks. We didn't manage to get human evaluation. Evaluate humans for everything, but we've got it for No Man's Sky, and we'll just compare the agent in No Man's Sky with humans in No Man's Sky to get an idea of overall where it is compared to humans. So first, this is the overall kind of, score normalized by the environment specialized agent. So the first thing we can see here is we have positive transfer. So an agent does better on some specific game if it is trained on information from other games. So it is actually generalizing between games. So information in No Man's Sky is helping in Valheim, for example. This is what this shows. And we do also see generalization. So we can see a zero-shot agent that has never seen a specific computer game does almost as well as an agent trained specifically on that computer game because of all the information it learned from the other games. So we have an agent that is managing to generalize its knowledge from one domain to another. And then, so these are just the standard good ablations. Pre-training really helps. It really helps that the agent got this kind of internet-level information beforehand. And then also, this was our sanity check. You don't get zero without language. The agent does a fairly good job of kind of guessing what thing you're supposed to do in a lot of the tasks. But still, this is definitely an agent that is benefiting from language. That much is clear. And now we can break down the performance a little bit by environment. So the first thing to say is we have positive transfer across all the environments. There's no environment where the simmer agent doesn't do better than the domain expert or the environment-specific agent. Again, generalization varies quite a lot by environment. Pre-training is always helpful, but to varying degrees. And then language always helps a lot. We can also see satisfactory, the no language agent does pretty well. This might be down to the kinds of tasks we put into satisfactory, and maybe we just need to think a little bit more about task design then. But still, there's benefit to language even there. So last thing, I mentioned classifier-free guidance a few slides ago, and say this was one of the single things that boosted agent performance the most. You can see here, CFG is very beneficial. But also that even without CFG, the agent still is learning a lot of language, but just it's really benefiting from the extra language conditionality that we get from classifier-free guidance. And now the human baseline comparison. So the first really interesting thing here is so most of these tasks are fairly simple instructions. It's things that we expect a person to be able to do in kind of normally 5 to 10 seconds, at most, say 30 seconds. But humans actually don't get 100% in this, which is interesting. I think a lot of it might be the time. They don't have that much time to do it. But also, I should also mention these are humans who have played the specific games before, so they should be reasonably good in it. But you get a language instruction, you need to parse it. Sometimes you might need to pick up a thing and accidentally misclick and run out of time. So that kind of puts the agent in a little bit of perspective. And we can see we're still not matching human performance. So this is, all those valuable jobs where people play games for a living, they're not about to be taken by this agent. You're better off using a human than this agent. But it's not that far. We're making reasonably good progress. But obviously, we're a long, long way from superhuman performance. So closing remarks. So we kind of feel like a lot of previous works in the AI field were kind of limited. They lack diversity in their trajectories. So a lot of games, they had one very, very specific goal, and they were just collecting trajectories towards that specific goal. Also in their observations and affordances. So there's been great work in Minecraft, but that agent is just learning Minecraft. It hasn't that limits what it can learn, as we've seen, because there's a lot of transfer between domains that you can get. And we think of the work we're doing on Simma very much as like the next generation in agent-based research, and we kind of put it in as we started in DeepMind with Atari, where you have a very, very specific goal that is maximizing some score, and it's an environment where there's very limited control. We got as far as like StarCraft 2, which is an amazing project, but again, it's just optimizing for beating a single opponent. And we think there's huge benefits if you're trying to build kind of superhuman agents in this approach where you give the agent kind of any task with any domain, and we've seen kind of very positive results from taking this approach. Yeah, and we hope the kind of simulation-based training is likely to lead to meaningful insights into creating AGI. We kind of see the place where Simma is as in the pre-training phase. So if anyone ever played around with ChatGPT 2 or maybe 3, like some of the earlier versions before they did a lot of the RLHF work, it was really amazing at the time, but it was kind of an amazing like toy, or even toy is maybe being a bit too kind. It was just an amazing curiosity. You could ask it to like generate a newspaper headline, and it would come up with something plausible, but it wasn't really useful at that point. It was just like kind of an interesting thing like that. And this is kind of where we feel Simma currently is. It's amazing in that we have these kind of wow moments sometimes when we're playtesting it, where we ask it to do a thing and it just knows. And here again, it's a video of it's asked to chop down a tree. It doesn't go to any of the big thick trees. It selects a nice thin tree and chops it down. So we're getting glimpses of this impressive capability, but it's still quite a long way from being the kind of general purpose super intelligence of some people's dreams. I don't want to speak for everyone. And yeah, we may be just and we think this is just a great test bed that kind of puts us maybe just like a handful of innovations away from something that is general purpose across all environments. We're very excited by the kind of work we've been doing, and very happy with how much support we've had from the games community and kind of helping us with playing on their games and things like that. And I'll leave with this quote from Jim Fan of NVIDIA. If an agent is able to master 10,000 diverse simulated realities, it may well generalize to our physical world, which is simply the 10,001st reality. And this is our beautiful team of people who worked on it. It's a very big team working just on this specific project. If you are after more details, if you found this interesting, we have a tech report and a blog post with a few more interesting details in it. And that is the end of the talk. Thank you very much. And I believe there should be good time for questions now, if anyone has any questions.
Thank you very much. It's a very interesting talk. Forgive me if this is a stupid question, but when you're going through the graphs, it looked like Satisfactory had quite a big standard deviation across quite a lot of the dimension, like going through. Could you talk maybe about why that might be?
Oh, that is such a good question, and I've not been asked it before, and I'm going to have to think on my feet, which is always a little annoying. Oh, well, okay, actually, I think Satisfactory has fewer tasks than some of the other ones. That is the first thing that comes to mind.
So the data's a bit more spiky?
Yes, and I'm trying to remember, it might be Satisfactory. We had a higher percentage of the tasks were human evals, and we didn't maybe get as many trajectories on those, but I'm not 100% sure about that. I think it might be that, though.
Thank you very much.
Hello.
Hi.
I'm wondering if you have any, if there's any relevance to, let's say, hidden currently, like real world environments to the way you train your agents.
Do you want to take that? Or I can take it. Yeah. So Pierre-Marie at the beginning kind of hinted a bit at robotic applications, and like we've had the quote from Jim Fan about bringing the agent into the real world. I think we haven't done any work on this yet, but I think we all have in mind we do want to put something like this inside the physical world at some point.
Sorry, I mean the exact opposite with like
training on real world data.
Yes. Which has, for example, the Philippines is made of 7,000 islands, and most of them are unmapped.
Yeah, that's definitely like a really, really interesting area of research. I think currently, so this is one of the advantages of simulation, is that it's so easy for us to generate kind of really diverse and interesting data. And because we have things like save games and computer games, you can like load to a particularly interesting state. I think the real world is like an incredibly the real world is interesting for data. It's like a really weird statement to make. But I think basically like right now it's a lot more expensive to collect data in the real world because you say the Philippines, we'd have to fly someone there with a camera or something. So right now for the Simmer project, we're much more focused on simulated domains. But the real world is definitely interesting.
Understood. Thank you.
Hi. First of all, thank you so much for sharing this information with us. I have a question, but I hope it's not too intrusive. I'm just curious. I assume that you guys must have fine-tuned an LLM for this. And is there like a base model that you used? And the data, like how many? You must have got a lot of data entries from across multiple different games. So I wonder, like, if you're able to share with us roughly how much samples you collected and what your base model is.
Yeah, so we didn't, so there's no LLM in this at all. So it's not on top of an LLM. So I mentioned, trying to get to the right slides. So we do have two significant pre-trained components. So neither of them are LLMs, but one is it's Spark. It's a clip style model. It's kind of matching images with text and some spatial information. And the other one is so Funaki is it's kind of like an early text to video model. So you can put in text and it will generate a video of that, and we use the encoding portion of that. Those will, I don't know precisely what those are trained on, but they will be trained on kind of internet scale data probably, or pretty diverse amounts of data. So that, and as you've seen, that definitely helped a lot. I think I'm not allowed to share exactly how much human data we collected. It's probably more than you think it is.
Yeah.
Hi there. I just want to say great talk from both of you. And is there a reason why you omitted Minecraft from your list of games you covered, considering you had previously done a paper on it and you might be able to compare results?
Yeah, I think we had in mind we wanted to do Minecraft at some point. And then obviously, you have only so many hours in the day. And if you do A, you can't do B. And we were kind of trying to onboard these different games at different rates. And then, it's not just a matter of like, you just immediately play, like we'd also need to build out tasks for Minecraft because we're doing quite a different thing. I can also say the agent probably would not do well at like collecting the gold. So there's a whole AI challenge that is how quick can you get an agent to collect the golden pickaxe in Minecraft? Our agent would probably not do well at that because it's trained to do a whole bunch of unrelated things, where if we were trying to do well at collecting the golden pickaxe, we would drop all the other stuff. So it's both, it would have taken us extra time to onboard it for the kind of thing we were doing. And then if we tried to get it to do the thing that a lot of the external benchmarks are in Minecraft, well, then we'd just be taking a very different path, and that would be a different project. So I think that's probably that. But okay, we have vague plans to put it on Minecraft at some point, maybe.
Okay.
Thank you. Fantastic talk. Privileged to hear. None of your verbs were social that I saw. You said we encompassed the dictionary. many people here would recognize the idea of socialization as being a task that is work. Is it a trivial problem to say, well, we just need to describe social interaction as tasks, and I don't want my tools to have feelings? Or is there a new sort of more complex or difficult set of problems that come when you start thinking about socialization as a mode of behavior for these agents?
Yeah, lovely question and very well phrased. Thank you. So I think talk is in there because like some of the games have NPCs and things like that. And again, this a bit comes down to like if you do A, you can't do B because of time in the day. So we've so far just focused on kind of single player experiences. It's really exciting, the idea of having more agents interacting with each other in social ways. We've also talked about putting humans in the game with the agent rather than controlling via language. But these things are like future things. Maybe
what we do in games isn't necessarily task oriented. It makes it expressive, or just wondering or wandering.
Yeah. That's all really interesting stuff that we'd the ultimate the.
It's on the roadmap.
Well, I don't want to overstate anything, but it's the kind of when we talk about the goal we have, an agent that can do everything, it definitely includes like socialization and things like that. Sorry, I think we're at time now. Very sorry. We can maybe talk after. Thank you very much, everyone.
Thank you.